Hello, I'm Ron Espiritu, and I work with the members on screen to complete the fifth design assignment of the semester. The goal of our assignment is to find the ideal bimorph bridge dimensions, which are its length, width, and height, that maximize the longevity of our bridge. The bridge is said to have two layers, quartz and titanium, and the longevity of our bridge is measured as in terms of its sensitivity, which is its relative change in resonant frequency per increase of deposit thickness. This deposit thickness refers to the thickness of the third material, which is either gold, molybdenum, chromium, or silicon dioxide, which gets deposited on the top of our bridge in the center. The length of this window is another dimension which we need to evaluate. Our system is considered to be functioning when its sensitivity is above 0.0002%. There are several constraints which keep our bridge within certain dimensions, one of the more important ones being that the bridge width is a quarter of its length. Furthermore, the ratio of the two layer thicknesses is to be one that produces the most strain under an electric field. I mainly focus on the building of the Python optimization and the analytical calculations. First, it's important to understand the geometry of our system. Our quartz layer, which is piezoelectric, is initially excited by an electric field, and as previously explained, we have a small window in which our deposit is to be placed. The main PDE we use is this equation, in which we solve for a modification of the previous dA's equation, where instead of setting the equation to 0, we set the equation to equal the mass density multiplied by the second derivative of the harmonic solution in order to find the transverse displacement of the beam at its resonance frequency. This equation is convenient for flex PDE since the solutions can easily be solved using modal analysis. Before we can calculate the geometry of our model, we must first solve for the ratio which produces the highest curvature. This is done by solving for the curvature equation parametrically, then plugging in the known values to find the curvature. The ratio of quartz to titanium was solved to be 1.228. It's also important to evaluate if it's possible to leverage symmetry. Because of the symmetry on the x-plane, it's possible to evaluate this problem only modeling half of the bridge. From there, the components of the bridge and their respective geometries were modeled leveraging a symmetry along its length. Then we moved into several test cases which were performed to build the validity of our flex model. Our first test checked if half of the bridge was modeled correctly with the modified boundary conditions, and if it did, then both of our full bridge and half bridge resonant frequencies should be the exact same when all the other parameters are held constant, which is the case as seen in these frequencies. We then place our bridge under no electric field and an electric field to see if it strains under a field, which it does. We then went on to test how the window thickness changes the resonant frequency, and it was observed that higher thicknesses decreases the frequency. This fits with our understanding that the stiffness of our beam, increasing the stiffness of our beam rather, will decrease the frequency. Moving into scripting, it's important to recall that our goal here is to find the dimensions that maximize the longevity of our system. And to do this, we built several different functions. We have the getFrequency function, which uses string manipulation to run the flex code given our dimensions, and returns the resonant frequency associated with those parameters. We have the getSensitivity function, which finds the sensitivity of a set of dimensions after increasing its deposit thickness by a small amount. We have the compareSensitivity function, which outputs the dimensions associated with the maximum sensitivity of our bridge. And we have the checkBounds function, which takes the past set of dimensions and makes sure it fits within the percent constraints defined previously. And finally, we have the untilFailure function, which takes a set of dimensions that produces the maximum sensitivity and increases its deposit thickness slowly until it fails. When they work in unison, they output the most ideal dimensions and the amount of deposit that was placed on it before it failed. Given the values, we were not able to find the amount of deposit placed on an ideal set of dimensions because FlexPDE gave an n-grid error prior to crossing below that sensitivity threshold. However, we can still extract information from the ideal dimensions for molybdenum, gold, chromium, and silicon dioxide. Molybdenum having the highest dimensions goes against our previous understanding that larger dimensions will decrease the change of sensitivity. However, it suggests that there is an ideal relative change in overall beam parameters that does maximize sensitivity. Gold, having the second highest dimensions, yet the lowest of all the Young's modulus, also supports this hypothesis. However, chromium and silicon dioxide having the same values may suggest that the sensitivity is dependent on the relationship between a material's Young modulus, mass density, and Poisson's ratio.